Hello everyone. Good afternoon to all of you. So I'm launching a poll. All of you please give me your class status. Okay, checking. So just let me know if I'm visible and audible. Yes. Am I not audible? Yes. Good afternoon, actually. Good afternoon. Sure, sure. Just wait for a second. Okay. So we are discussing about the physical properties and its strengths, right? So there were four physical properties I told you. First one is atomic and ionic radius. Second is ionization enthalpy. Third is electron gain enthalpy. And the fourth one is electronegativity. Okay. So in the last class, we have discussed the atomic and ionic radii in detail, right? So now let me give you a previous year question as a recall test from the atomic and ionic radius topic. All of you try this question and give me your answer in the chat box. The question says that the species argon, potassium plus and calcium 2 plus contain the same number of electrons. In which order do their radii increase? So we have three species. We need to find out the correct increasing order of the atomic radius. Okay. So all of you apply the concept we have studied. And in the question itself, they are saying that all the three have same number of electrons. So what is the meaning of same number of electrons containing species? They are isoelectronic species, right? So what is the, how to find out the order for isoelectronic species? Yes, very good, very good. Both of you have given me the correct answer. Option A is correct, right? So how to find out what is the relationship we have to use here? Ionic radii or the atomic radii. Ionic radii is inversely proportional to the atomic number, right? So this is a relation which we have to use. So if you look into the calcium 2 plus, the atomic number of calcium is 20. And for potassium, it is 19. And for argon, it is 18. Okay, but potassium has lost 2 electrons, so 20 minus 2 will be 18. Potassium has lost 1 electron, so 19 minus 1 is 18. And here argon is in 0 state only. So the total number of electrons will be 18. So all the three have the same number of electrons. So that's why we are calling them as isoelectronic species thing. Okay. Now the one which is having the lowest atomic number will have the largest ionic radii. So that's why argon, then potassium, then calcium. Okay. So option A is the correct answer. So now let me go for the second physical property, which is ionization enthalpy. Okay. So let's go for this. So to study the ionization enthalpy, I would like to take an atom, and this is a sodium atom, which is in isolated gaseous form. And we all know that sodium has 11 electrons, as its atomic number is 11. And there are 2 electrons in the first shell and 8 electrons in the second shell. And the last 11th electron is present in the third shell. Okay. So the electron which is present in the outermost shell, okay, is 1. The number of electrons present in the outermost shell for sodium is 1. If I want to remove the electron which is present in that outermost shell, and also I am removing that electron. So this loss of electron thing will lead to this type of configuration for sodium, right? Sodium, after losing 1 electron, it will be converted to sodium plus. So if you want to take out an electron from an atom, you need to supply some energy, right? So the energy required to remove the electron from isolated gaseous atom in its ground state is called as ionization energy. Okay. So just like that, simply you cannot remove some electron. You need to give some energy to remove the electron. Okay. So that energy is called as ionization energy. So since I am removing the first electron from this atom, it is called as first ionization enthalpy, which is denoted by delta H1I. Okay. And mathematically, if I want to denote this ionization enthalpy process, I can denote like this. Okay, what is it? I have an atom called X in gaseous state, and I have removed 1 electron from that X, and that X has been converted to X plus. Okay, and the atom is absorbing the energy which I am giving, right? The atom is absorbing the energy which I am giving. So this is an energy absorption process. Energy absorption process. So it will always be endothermic. Ionization enthalpy is an endothermic process because the energy is getting absorbed by the atom. If it is an endothermic process, then the delta H value will be positive. Delta H value will be the change in enthalpy value will always be positive for endothermic process. Okay. So ionization enthalpy are always positive as the energy is always required. Clear for all of you? Any doubt from this? Shall I go for the next? Is it clear to all of you guys? Let me know fast in the chat box so that I can proceed further. Very good. Very good, Harman. So it is clear. So let me go for one more atom. So here I am taking magnesium. And all of you know that the atomic number of magnesium is 12. And there will be 2 electrons present in the outermost shell. So the shell electronic distribution will be 2, 8 and 2, right? So there are 2 electrons present in the outer shell. So these are those 2 electrons. And first of all, what I need to do? I have to remove the first electron. For example, let me say I'm going to remove this electron. And loss of this 1 electron will lead to Mg plus configuration. And also I have 1 more electron in the outermost shell. And if that electron also gets lost, I will get this type of configuration with Mg2 plus. Okay. So the energy associated with the removal of first electron is called as first ionization energy, delta H1. And the second is, and the removal of second electron is called as delta H2, which is called as second ionization enthalpy. Okay. So the first atom will have the less nuclear charge and Mg plus will have more nuclear charge. So if the system is having more nuclear charge, then more amount of energy is required. What is meant by nuclear charge? the charge which is present inside the nucleus. So what are the charges present inside the nucleus? So this is the nucleus. Inside the nucleus, we have protons and neutrons. Protons are positively charged species and neutrons are neutral. So 0. Okay. So inside the nucleus, I have the positive charge. So that proton charge, which is positive, is called as nuclear charge. Since we are removing the electron here, one electron is getting removed. So, but the proton number will remain same. Here I will have 12 proton and 12 electron in case of magnesium. But in case of magnesium plus, I will have 12 proton but only 11 electron. Okay. So, the nuclear charge is more. Nuclear charge is more. So, more amount of energy is required to remove the electron from the system which has more nuclear charge. Okay. So, the second ionization energy will be more compared to the first ionization energy. The removal of electron from the ion is more compared to the removal of electron from a normal neutral atom. Okay. The removal of electron from a cation is more compared to the removal of electron from a neutral atom. Got it? So this is the mathematical denotation. And if we are asked to find out the ionization enthalpy for magnesium, then we have to add the two values. Okay, we have to add the two values. So now let us go for the trend of this ionization enthalpy. Okay, so let me take a graph. So what do you observe in this graph? So the graph has some peak points and also the lowermost minimas and maximas we have, right? So the maximas are occupied by a particular group and the minimas are occupied by the another group. So can you tell me the maximas are occupied by which group? We have 18 groups in the periodic table, right? Helium, neon, argon, krypton, and xenon. So these elements belongs to which group in the periodic table? Very good. Group number 18, which are called as noble gases. So the maximas are at the noble gases. Okay. So it means that for a particular period, the noble gas is having the highest ionization energy. Okay. Suppose for example, if I take the second period element, second period starts with lithium and it keeps on going. Beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So this is the second period element which starts with lithium and ends with neon. Got it? So the lithium is having the lowest ionization energy which is 500 kilojoule per mole and the neon is having somewhat around 2400 kilojoule per mole. So in a particular period means if I am going from left to right in the periodic table, the noble gases are having the highest ionization energy because of the fully filled stable electronic configuration. You all know, right? So the noble gases will have the completely filled shell. So it neither loses its electron nor gains some electron. And if I want to remove an electron from an noble gas, I have to give more amount of energy because it is completely filled, which is stable. So if you want to disturb the noble gas, it becomes very difficult. Okay. So it requires a high amount of ionization energy. So that's why the topmost point is occupied by noble gases for all the periods. Got it? And also the lowermost minimas are at the alkali metals. Lithium, sodium, potassium, rubidium, cesium, and all these elements which are occupying the minimum position, if you look into it, they are actually alkali metals, and alkali metals belongs to which group? First group, which has NS1 configuration. So if they lose this one electron, they will attain the noble gas configuration, the filled configuration, right? Like if I have sodium after giving out one electron, it is becoming sodium plus. Sodium plus is having 2 and 8 electrons. which is actually the configuration of neon, and it is a noble gas. So after losing one electron, the alkali metals are getting the or attaining the noble gas configuration. Because of this, the energy required to remove the electron from them is becoming very easy, which is nothing but the ionization is very less. So the reactivity will be very, very high. You need some energy to remove the electron, right? Just like that, how it will not come out. We only have to remove by giving some energy, right? Harmit Trivedi, yeah, getting. So it won't just come out of its own. It will attain the stability, but the energy required is very less. You got it? Very good. So immediately it will react. Okay, immediately it will react. So that's why high reactivity and less amount of lowest ionization energy. Okay. So what do we observe from this? Across the period, ionization energy increases. Across the period, you see here, from lithium to neon, if I go, ionization energy on going from left to right or across the period, it increases. You all know why it increases, right? I told you. Electrons are added into the same shell. If I take lithium, this is lithium and this is beryllium. All of you know that across the period size decreases, right? So this is boron and carbon will be still smaller in size. So this is the nucleus of lithium, nucleus of beryllium, nucleus of boron, etc. And all of them belongs to the second period. So this is shell number 1, this is shell number 2. Here, this is shell number 1 and this is shell number 2. So what happens here? In case of lithium, we have only one electron in the outermost shell. In case of beryllium, we have 2 electrons. In case of boron, we will have 3 electrons in the outermost shell. So what will happen? The electron will get attracted towards the nucleus. So as we go across the period, more number of electrons are occupying the outermost shell, which increases the attraction between the nucleus and the outermost electron. So because of that, size is decreasing. It means attraction is more. So I have to give more amount of energy to remove an electron which is smaller in size. Got it? So that's why across the period the ionization energy increases. Since the electrons are getting added into the same shell, which leads to more attraction. Got it? Shall I go for the next? Any doubt from this for anyone? Everything clear? Across the period, ionization energy increases. Then coming to the next group, group trend. So I'll take one more graph. So this is the graph for group 1 elements, which is starting from lithium and ending with cesium. So this is on moving down the group. On moving down the group, what will happen? The shielding of valence electron increases and ionization energy decreases. So you know this is the size of lithium, sodium, potassium, rubidium, cesium. Like this, it goes on. So the distance between the nucleus and the outermost shell, the distance between the nucleus and the outermost shell is more, right? So we can easily remove an electron from the last case compared to the first case. So what is happening? Ionization energy is decreasing. Okay. So if the electron is very far away from the nucleus, you can easily remove that particular electron. So that is the concept. You don't have to give more energy to remove that electron. Less amount of energy itself enough to remove the electron. So on moving down the group, it decreases and across the period, it increases. So this is the trend we observe for ionization enthalpy, and this is the general trend. Okay, this is the general trend. we do have some anomalies. Anomalies means some kind of exceptional things. Okay, some kind of exceptional things due to some reasons. So that anomaly property I will discuss in the next slide. So you see here, let's go for the anomalies in trend of ionization enthalpy. So I am going to take this first graph across the period graph. Okay, here in this graph, if you observe the ionization energy of beryllium and boron, what do you observe here? What is the ionization energy of beryllium? It is 899, and for boron, it is 801, right? Yeah. Can you tell me why boron is having the lesser ionization enthalpy compared to beryllium? So according to the general trend, boron should have the highest value because across the period, the ionization enthalpy should increase. But beryllium is having the highest value compared to boron. Why? What could be the reason? Can anyone give me the reason for this? Can anyone give me the reason for this? Okay, I'll tell you. Let me take the electronic configuration. Okay. So this is the balanced electronic configuration of beryllium. You all know that beryllium's atomic number is 4 and the electronic configuration is 1s2, 2s2. So this is the valence electronic configuration of beryllium, which is 2s2. And when you look into the boron, boron's atomic number is 5. Electronic configuration is 1s2, 2s2, 2p1. So second shell is the valence shell and it has 2s2, 2p1 configuration. Okay. Now, the energy required to remove the electron from the p orbital is less compared to s electron. That is, the removal of electron from p orbital is easy as compared to s orbital. So that's why we can able to remove the electron from boron so easily compared to beryllium. So ionization energy is becoming less for boron compared to beryllium. Okay, because of the fully filled configuration and the shielding effect. Shielding effect, I can say. Somebody wants to say something?
Chat. Video na.
Sai Jashwant, you want to say something?
Problem. Sabi ka siguro po.
Sai Jashwant from JNB Kurnool. Okay. So have you all understood this concept? The removal of p electron is easy, so that's why ionization energy is very less. Shall I go for the next anomaly? Yes. Is it clear? Okay. All of you try to give your answer in the chat box, okay? You don't have to get scared. I already told, no? You don't have to get scared. Just try to interact in the class. It will be very, what to say, very good, no, in the classroom if you are interacting, all of you. Yeah. Yeah, I'll go for the second anomaly. So this is the graph. And here if you observe for nitrogen and oxygen should have the highest value because its atomic number is 8 and nitrogen should have the lowest value. But it is the other way around. Nitrogen is having the highest value compared to oxygen. Why? So this is because of the stability. So let me take the electronic configuration of nitrogen. Yeah, very good. So this is the configuration of nitrogen. 2s2, 1s2, 2s2, 2p3 and this is the outermost configuration. Okay. Yes, Harmit, very good. Your answer is exactly correct. And coming to oxygen, the configuration is 1s2, 2s2, 2p4. Okay. So nitrogen is having 2p3, oxygen is having 2p4. If there are 3 electrons present in the p orbital, having one electron in each orbital, it is actually called as the half-filled configuration for the p orbital. Okay. So half-filled configurations are more stable compared to the partially filled configuration. Partially means instead of half-filled and fully filled, if you have some other configuration in between, it is called as partially filled. Okay. So here in case of 2p4, it is called as partially filled configuration and nitrogen is half filled. So it is stable. The one which is having the half filled configuration is more stable. So the energy required to remove the electron from more stable configuration is more. Okay. Clear? Extra stable half filled electronic configuration. And here there will be repulsion in case of oxygen. So since because of the stability, nitrogen is having the highest ionization enthalpy value. Okay. So shall I go for one previous year question from this concept? Is it clear to all of you? Yes. So all of you try to solve this question. The correct order of first ionization enthalpy for the given 4 elements is, we have only 4 elements, okay, but we have many elements, no, in the second period: lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So these are the elements present in the second period. Okay, option C or option D, which one is correct? So here, okay, all of you first try, give me the correct answer in the chat box, then I will discuss. First, option D. Varalakshmi is going for C. CONF. Dhruvi is going for C. Why some of you are going for C? Sanket is also going for C. All of you think wisely. We have seen 2 exceptional things, right? This is actually according to the trend, listen, according to the trend across the period, ionization energy increases. Means this should be the correct order. Okay, or I can say that this is the expected order for second period elements. Okay, but we do have some anomalies, right? The beryllium and boron has some anomaly and nitrogen and oxygen have some exception. We have to interchange. So what we have to do? Lithium will be there, but in place of beryllium, you have to put boron, then beryllium, carbon, and here oxygen, then nitrogen, fluorine and neon. Okay, you have to just interchange these two. You have to just interchange these two. And this is the observed order. This is the observed order for the second period elements. Okay. So in the question, you need to answer in accordance with the observed value only. Got it? So in the question, how many elements? What are the 4 elements we have? We have carbon, oxygen, nitrogen, and fluorine. We have these 4 elements. So now which is the correct answer? Option D, right? Option D is the correct answer, no? So you just need to apply the concepts which you have studied. Okay. So this question has been asked in many exams in many years. Okay. Most of the years they have asked this question. In 2019, NEET also we have got this, and this was the question asked in some other year in JEE. So you need to apply the concepts which you have studied. Is it clear and all right for all the students who have opted for option C? Are you all clear now? Clear? Sanket, Varalakshmi, is everything okay now? So hereafter you guys won't make the same mistake, no? Okay. So this is all about the ionization enthalpy. The next is electron gain enthalpy. What is electron gain enthalpy? So let me take an atom. I'm going to take fluorine, which has the atomic number 9, and the electronic distribution will be 2 and 7 in the shell. So the outermost shell has 7 electrons, and if it gains 1 electron, it will attain the noble gas configuration, which is fully filled configuration. So what it will do, it will gain 1 electron from outside, and it will get converted to F minus. If something is gaining an electron, it will become an anion, right? So F will be converted to F minus. So when this fluorine atom gains 1 electron from outside, some amount of energy will be released. Amount of energy will be released from that atom, and that energy or that enthalpy is called as electron gain enthalpy. Got it? Suppose you are standing here, okay, and somebody is standing here. Okay, person one is standing here and person two is here. Person two is having a stone in his hand. Okay, so this person two is throwing that stone into the head of this person one. Will this person one stay calm and quiet, or he will shout? Tell me, will he shout or he will stay quiet? He will shout, right? If he is shouting, energy will be released and he will go to the higher energy state, which is actually the unstable state. The same thing happens here also. An atom is there, an atom is there. We are throwing the electron. We are putting an electron from outside to this atom. Okay? And during that time, some amount of energy will be released from that atom, and that energy exchanged when an electron is added to an isolated gaseous atom in its ground state is called as electron gain enthalpy. Okay. Since this is actually the gain of the first electron, it is called as first electron gain enthalpy, and mathematically it is denoted like this. An atom called X is gaining 1 electron and it is getting converted to an anion with X minus formula. Clear for all of you? This is the concept. Now we'll go for the trend. Any doubt in the concept for anyone? Shall I proceed? Shall I proceed with the trend? Yes or no? First. Okay, yes. Thank you. So now let's discuss the trend of electron gain enthalpy across the period. Across the period. So I'll take some periods, okay? Group 1, group 16 and group 17 I have taken. And we are going to study the trend for these three groups across the period. So let me take the second period. Second period has lithium, oxygen and fluorine. Okay. So what do you observe here? One more thing I want to tell. Let me explain that and come back here, okay? Yeah. So since the electron is getting also, I mean the energy is getting released from the atom, right? The energy is getting released from the atom. The energy is getting released from the atom for this electron gain enthalpy process. So this process is exothermic in nature. If energy is released from an atom, it is exothermic in nature. If it is exothermic in nature, delta H value will be negative. Okay. just the opposite of ionization enthalpy. That is endothermic because energy is observed. Here exothermic because energy is released from the atom. Okay, there it is positive and here it is negative. This negative sign denotes that the energy is getting released. That's all. Okay, negative sign denotes that the energy is getting released. Okay, you should not take this completely like you are taking in max. Okay, the negative sign denotes just the energy releasing process. Otherwise, you should forget that. You just look into the values alone. Okay, all of you just see the values alone. So, what do we have for lithium? 60, and for oxygen it is 141, and for fluorine it is 328. So just by seeing these three numbers alone, what is the trend we have across the period for electron gain enthalpy? Is it increasing or decreasing? What do you guys say? It increases or decreases? 60, 141, 328. Tell me, is it increasing or decreasing? Very easy, no? Across the period from left to right. I'm waiting for your answer. Very good. Very good, Sri Lakshmi. It is increasing. So across the period, very good, Dhruvi. Across the period, electron gain enthalpy increases. Very good, Bindu. Across the period, electron gain enthalpy increases. Got it? It increases across the period. And if you see to the group 17 elements, they are having exceptionally the high negative electron gain enthalpy. More negative. More negative or the highest value for electron gain enthalpy. If the value is very high or if something is having the more negative electron gain enthalpy, then it means that we can easily add an electron to that atom. Okay. If an atom is having more negative electron gain enthalpy, or if the electron gain enthalpy value is very high for an atom, then it means that you can easily add an electron to that species. Got it? So here F is having the highest value. Means I can able to add an electron easily so that it becomes F minus and becomes stable. Clear? So on going from left to right, the ionization energy, the electron gain enthalpy increases. Clear for all of you? Shall I go for the trend on moving down the group? Across the period trend is clear to all of you, right? Now let's discuss the group wise trend. Yeah. So let me take three groups. Group 16, group 17 and group 18. And what do you observe for these three groups on moving down the group? Is it increasing or decreasing? Is it increasing or decreasing? Just don't think of this oxygen, sulfur, fluorine, chlorine values for now. I will come to that part later. You start from sulfur and here you start from chlorine. Now you tell me the trend you observe for these two. You should not consider the negative sign also. Okay? Yes. On moving down the group, electron gain enthalpy value decreases. It decreases. So the general trend is across the period increases, on moving down the group decreases. Okay. So now we will discuss about the oxygen, sulfur and fluorine, chlorine story, which is actually an anomaly. Anomaly means something which is irregular. Okay, which is not following the regular trend is called as anomaly. Exceptional case. If you go from oxygen to sulfur, on moving down the group, it should decrease, right? But when you go from oxygen to sulfur, it is increasing. So oxygen is having the less value compared to sulfur. The same way in case of fluorine and chlorine, chlorine is having the highest value compared to fluorine. Why? What is the reason? The reason is the size factor. Okay. Oxygen and sulfur, if I compare, oxygen will have the smallest size. And if I compare fluorine and chlorine, fluorine will have the smallest size. Otherwise, no, Varalakshmi, you don't have to memorize the values. You don't have to memorize the values. Okay. Memorizing these values is of no use only. So they will not ask you to find out the values in the examinations. Okay. It's of no use. You don't have to memorize. Just think of the trend and learn the anomalies alone. Okay. You need to know the reason, like why it is having the less value, why it is having the highest value, why it is decreasing, and why it is increasing kind of reason you should know. You don't have to memorize. Okay. Okay. Let me come to the reason now. The size of the fluorine or the size of the oxygen is so small that electron cloud at fluorine or electron cloud at oxygen causes repulsion with the incoming electron. What is the meaning? What they are trying to say? So I'll go for the orbital. Oxygen will have 2p orbital and sulfur will have 3p orbital. So 2p orbital will be smaller in size compared to 3p orbital, right? Oxygen is the second period element, so it is having only the last electron in 2p orbital. Sulfur belongs to third period, so it will have 3p orbital. So in the same manner, fluorine will have 2p orbital and the chlorine will have 3p orbital, which is bigger in size. And in 2p and 3p orbital, we already have some electrons, right? So oxygen and sulfur belongs to 16th group and they will have four electrons in their 2p and 3p orbitals already. And if I go for 17th group fluorine chlorine, they will have 5 electrons. 1s2, 2s2, 2p, 5, right? So they will have 5 electrons in their 2p and 3p orbital. Okay. So these are the electrons which is already present inside the inside the orbitals. Now what is electron gain enthalpy? Adding an electron Adding an electron to an atom is called as electron gain enthalpy. So suppose if I am going to add one electron to this fluorine and also I am going to add one electron to the chlorine. So the space in case of chlorine is very high, very big. The size of the orbital is big. So the incoming electron will not observe that much of repulsion with the electron which is already present inside that orbital. Okay. In the same way, for fluorine, we have 5 electrons and the electron which we are going to add, which is actually called as the incoming electron. So that will suffer more repulsion because the size is very less. Okay. The space given for occupying this 5 electrons is very less. So if I add one more electron, already 5 electrons are there. So that those electrons will repel with this incoming new electron more. So in that case, the energy will go high. The energy will go high. So the addition of electron becomes difficult in case of the small sized atom like oxygen and fluorine compared to sulfur and chlorine. Clear? So you can easily add an electron to the one which is having the largest space compared to the one which is having the smallest space. So that's why the value is very less for fluorine and oxygen and it is very high for sulfur and chlorine. So if the value is very high, I told you that we can easily add an electron. Okay? Clear for all of you? Any doubt from this? So if they are going to ask you the order of electron gain enthalpy for these 4 species, what you have to do? Chlorine will have the highest value, then fluorine, then sulfur, then oxygen. Okay. So this is the correct order of electron gain enthalpy for these 4 elements. Clear? Is it clear to all of you? Any doubt from this for anyone? students? Is it clear? Just say yes or no in the chat box. Shall I go for the fourth physical property? Okay. Thank you so much for your response. Now I'll go to the fourth physical property, which is called as electronegativity. Okay. What is electronegativity? Ability of an atom to attract the shared pair of electrons in a bond of molecule. So I'm going to have a molecule and there is one bond between those two molecules. Okay. Between the two atoms. Suppose green is atom A and pink is atom B. Okay. So there are two electrons in between those two atoms which is forming the bond. The ability of one particular atom to attract the shared pair of electrons towards itself is called as electronegativity. Okay. So here atom B is having the strong pull because this first electron belongs to atom A and the second electron belongs to atom B. But atom B, what it is doing? It is pulling the electron of A also towards itself. Okay. So atom B is called as a more electronegative atom. The tendency of an atom to attract the shared pair of electrons towards itself is called as electronegativity. Okay. Now, to find out the element which is more electronegative in nature, scientists have came up with some numerical scales. Okay, so numerical scales of electronegativity of elements were there. So there were three scales actually. I'll give you the two scales alone. One is called as Mulliken-Jaffe scale, and the other one is called as Pauling scale. So we are using this Pauling scale of electronegativity only. Okay. So the Pauling scale in the Pauling scale of electronegativity, the number 4 is given to the element fluorine. And this fluorine element is the most electronegative element in the periodic table. Okay. So in the Pauling scale, the fluorine was given with the value 4.0. Clear? Yeah. Fluorine is the most electronegative element. Now we will see the trend. Now we will see the trend in electronegativity across the period. So we have, let me take two periods. Period 2 and period 3. So what do you observe here? 4.0 is given for fluorine and 3.5 for oxygen, 3.0, 3.0 for nitrogen and chlorine. Okay, and lithium is having 1.0. So across the period, what is the trend you observe? Is the value getting increased or decreased? Yeah, electronegativity increases across the period. Okay, electronegativity increases across the period. Fluorine is the first most electronegative element. Okay, first most electronegative. Oxygen is the second most electronegative element. Nitrogen and chlorine are the third most electronegative element in the whole periodic table. Okay, so you should know or you should memorize these things. So first is fluorine, second is oxygen, third is nitrogen and chlorine. Clear for all of you? So this is the trend you should observe for electronegativity across the period. Now I'll go for the trend in electronegativity on moving down the group. So I'll take two groups, group 1 and group 17. Yeah, very good, Harmit. So on moving down the group, electronegativity decreases. Okay, electronegativity decreases. Just the opposite. Very good, Vikas. So this is all about the electronegativity, which is very easy. So now let me summarize the physical properties. So first physical property was atomic radii. And while going from left to right, it decreases. And if I go from top to bottom in a group, it increases. And when I talk about ionization enthalpy, it is just the opposite of atomic radius, which increases across the period and decreases on moving down the group. And electronegativity also shows a similar trend, increases across the period and decreases on moving down the group. Now, if I come to the electron gain enthalpy property, it is more negative across the period and less negative on moving down the group. Okay, so actually, let me go for the physical property, and across the period and on moving down the group. So the first physical property is atomic size or atomic radius. It decreases across the period and increases on moving down the group. The second one is ionization enthalpy. Third is electron gain enthalpy. The fourth one is electronegativity. The other three is just the opposite. Increases across the period and decreases on moving down the group. Okay. So this is the general trend. This is the general trend we observe for the four physical property. Is it clear to all of you? And also we have discussed some exceptional cases in the name of anomalies while discussing each and every property. Is it clear to all of you? Any doubt from the physical property and its trend for anyone? Any doubt? Okay, shall I take 10 more minutes? Shall I take 10 more minutes? Shall I discuss the chemical properties for 10 more minutes? Are you all available? Okay. Varalakshmi is giving yes. Okay. So without wasting much time, I would like to enter into the trends in chemical properties of elements. So far, we have studied about the physical properties and its trends. Now, in chemical properties, I am going to discuss the periodicity of oxidation state, chemical reactivity, and the anomalous behavior of second period elements. Okay, so let me go into the first subtopic, which is periodicity of oxidation state. So before moving into the definition of oxidation state, I would like to take a term called valency. Valency. What is valency? It is the number of electrons present in the outermost orbital. Number of electrons present in the outermost orbital. Suppose if I take some groups from group 1 to, then I take group 13, 14, 15, 16, 17, 18. So the number of valence electrons present in each case is given and the valency is also given. Okay, the number of electrons in the outermost orbital is called as valency. Suppose if I take the second period element, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. So carbon is having the valency 4, nitrogen is having valency 3 or 5. 3 is the empty space that the nitrogen has and 5 is the number of electrons present in the outermost orbital. Number of electrons present in the outermost orbital of nitrogen. So in the same way for oxygen also, 2 is the empty space and 6 is the number of electrons present in the outermost shell. Okay, so it is the same for fluorine neon also. Now, what is oxidation state? The charge acquired by its atom after electronegative consideration from other atom is called as the oxidation state. Suppose let me take one example, okay, so that you will understand. I'll take OF2 compound, OF2. Now here I have two atoms of fluorine and one atom of oxygen and I have two bonds. Okay. Oxygen has 6 valence electrons. Oxygen has 6 valence electrons. 2 electrons has been used for bonding and the remaining 4 is present as 2 lone pair. Okay. Now coming to this electronegative consideration, I have 2 bonds. I have 2 bonds. And in both the bond, I have oxygen and fluorine. Which one is more electronegative? Oxygen or fluorine? Which is the most electronegative element among these two? Oxygen or fluorine? Yeah, it is fluorine, right? So what this fluorine will do in terms of electronegativity? What it will do? If I go for this first bond, this fluorine, since fluorine is more electronegative, there are 2 electrons here. One belongs to fluorine and the other one belongs to oxygen. So this fluorine, since it is more electronegative, it will pull the electron of oxygen also towards itself. So it is gaining the electron of oxygen. So it will get -1 charge and oxygen will get +1 charge. Yeah, it will pull the electrons towards itself. And with respect to the second bond also, fluorine will have -1 charge and oxygen will have +1 charge. Now oxygen in total, what is the charge acquired by oxygen in total? 2, right? The oxidation state of oxygen is +2. Now you come to this definition. The charge acquired by the atom after electronegativity consideration from other atom is called as the oxidation state of the element. Okay. Now all of you tell me the oxidation state of fluorine. What is the oxidation state of fluorine? You have to consider for one fluorine only. Okay, you have to consider for one fluorine only. Charge acquired by one atom. What is the oxidation state of fluorine? For oxygen, I told you it is +2. Yeah, very good. For fluorine, it is -1. Oxidation state of fluorine is -1. Is it clear? So I am taking this carbon dioxide compound. So I have two bonds. Oxygen is more electronegative compared to carbon. So the 2 electrons are gained by oxygen and lost by carbon. And with respect to the right side bond, oxygen will gain 2 electrons and carbon will lose 4 electrons. So the charge acquired by each oxygen is -2. The charge acquired by one carbon atom is +4. Oxidation state of oxygen is -2 here, and for carbon it is +4. Okay. So oxygen shows 2 different oxidation state in different compounds. In the previous case, oxygen had +2. Now in this case, it is having -2. So it is showing 2 different oxidation state in both the compounds. How to find out in which compound it will show positive oxidation state and in this compound it will show negative oxidation? How will you find out? You have to find out just by looking into the compound. So if oxygen is bonded with the fluorine, it will have the positive oxidation number. Okay, because fluorine is the only element which is more electronegative compared to oxygen. So if it is bonded with fluorine, oxygen will lose the electron and it will have the positive oxidation state. Okay. Rest all compounds will have the negative oxidation value for oxygen. In case of carbon dioxide, we have -2, right? So the more electronegative element will show negative oxidation state and the less electronegative element will show positive oxidation state. And also I'll tell you, only 2 compounds are there in which the oxygen is bonded with fluorine. One is OF2 and the other one is O2F2. So these are the 2 compounds in which the oxidation state of oxygen is positive. In case of OF2, oxidation state of oxygen is +2. In case of O2F2, oxidation state of each oxygen is +1. Rest all will have the negative oxidation state only. So these 2 compounds are called as oxyfluorocompounds. These 2 compounds are called as oxyfluorocompounds. Clear? This is all about the periodicity of oxidation state. Next is chemical reactivity. Let me complete this chemical reactivity part alone. The third part I will discuss in the next session, okay? So if I take a periodic table, the left side elements, which are actually called as metals, they can easily lose the electron, and the elements which are present in the right side, which are called as non-metals, they can easily gain the electron. Suppose for example, I have sodium here. Sodium will easily lose an electron and it will be converted to Na plus. And if I take fluorine, chlorine, so chlorine will gain one electron and it will exist in Cl minus. Okay. So now the reactivity of metals alone, if you compare, it increases on moving down the group. If I compare lithium, sodium, potassium, rubidium, cesium, and strontium, so cesium will be more reactive compared to rubidium. Rubidium will be more reactive compared to potassium. So like that, the reactivity of metals increases on moving down the group. In the other way around, the reactivity of non-metals increases across the period. Reactivity of non-metals increases across the period. Okay. So this is about the reactivity of metals and non-metals. The next classification is the nature of oxides. The metals or the left side elements reacts with oxygen to form basic oxide of formula Na2O, and the non-metals will react with oxygen to form acidic oxides. So here sodium is the metal and chlorine is the non-metal. Sodium is forming basic oxide, chlorine is forming acidic oxide. Left side, right side. And some elements are present in between, right? If I go for aluminium, it occupies group 13. Arsenic occupies here. So the elements which are present in the middle of the periodic table, they form oxides of this type, which is called as amphoteric oxides. Only two oxides are amphoteric in nature, aluminium oxide, arsenic oxide. Then the last category is neutral oxides. Okay, CO, NO, N2O. So these three will fall under neutral. So what you have to do, they will ask questions in the match the following type from this. Okay. So you should know which is a basic oxide. You should know which is an acidic oxide. You should know which two oxides are amphoteric, and you should know which of the three are neutral oxides. Okay. So they will give acidic, basic, amphoteric, neutral in one side, and the examples on the other side, and they will ask you to match it. Okay. So these are the oxides given in the book. So you should memorize this and keep this in your mind. Okay. Don't forget. So this is all about the chemical reactivity. Okay. This is all about the Varalakshmi, metals reactivity increases down the group because they are becoming more electropositive. If I'm going from left to right, electronegativity increases, right? So in the same way, electropositivity increases on moving down the group. If electropositivity increases, then that particular metal will be more reactive in nature. It will lose its electron more readily compared to the element which is above. Like if I compare sodium and cesium, cesium is highly reactive. It means that cesium can easily lose its electron. Okay, means the ionization energy will be very less for cesium compared to sodium because of its size factor. Got it? Yeah. Zinc oxide is also amphoteric only. Zinc oxide is also amphoteric, but those will come in your D block elements part. Here we are not considering the D block oxides. Okay, only the S block and P block we are considering. Okay, students, this is all for today. So we have one small topic left here in this lesson. which is the anomalous properties of second period elements. So that we will discuss in the next class. Okay. So thank you so much for attending the today's lecture. So before ending up the session, I would like to launch a poll. All of you please answer for that, and then you can leave the call. Okay. So thank you so much for listening the lecture. See you all. Take care. Bye bye. Thank you. Thank you so much.